A set is nothing but a collection of objects. It could be a collection of letters, it could be a collection of colors, numbers, just anything. In math, obviously, we're interested in collections of numbers. So, for example, if I can list the objects, the vowels, for example, A, E, I, O, U. This is listable. If it's listable, then we use these types of brackets and the objects are separated by commas. So if I say the set of all even numbers, it would be, let's say, positive even numbers. I could have a 0, for example, 2, 4, 6, 8. It is listable, and then I put the dots, so the pattern continues, and then I close the brackets. So this is a collection of numbers, and these are even numbers. A collection of odd numbers is also listable. 1, 3, we're looking at positive odd numbers. 1, 3, 5, 7, 9, and then I can go dot dot dot. And if it's listable, this is how I write it, with the curly brackets. Now these sets, let's say the set E of even numbers, the set O of odd numbers, it's listable, and there are infinitely many elements in the set. Elements are these objects that are sitting inside the set. So there are infinitely many, so it's an infinite set. If you look at the set of vowels, it's a finite set because there are just 5 in there. If there's a limited number, then it's finite. If the set goes on and on indefinitely, then it's an infinite set. Now the standard sets that we look at in math is the set of natural numbers or counting numbers. Starts with a 1. It's listable because it's 1, 2, 3, 4, and then the list goes on and on. It's an infinite set. The set of whole numbers is a set, again listable, starts with a 0, and then 1, 2, 3, and it goes on and on. The set of integers, you could call it I, or sometimes you'll see it as a Z, is dot dot dot. There are negative integers, -3, -2, -1, 0, 1, 2, 3, dot dot dot. Another way of writing this would be 0, comma, plus or minus 1, plus or minus 2, plus or minus 3, and so on. And then the set of rational numbers, any number that can be written as a P over a Q, like a fraction, such that the letters P and Q belong to the set of integers. And one more important thing is that the denominator cannot be equal to 0. So this is called the set notation. So the symbols that we use to describe the numbers in the set, we use the notation, and it's called the set notation. Anything that's not rational, so numbers included in this rational set of all rational numbers is just a few examples. Any whole number, any integer, let's say for example -2. -2 can be written as a fraction, -2 over +1. So it's like a P over a Q, where Q is not equal to 0. P is an integer, Q is an integer, so therefore this is a rational number. So any whole number, positive or negative is a rational number. 0 is a rational number because I can write it as 0 over anything that's non-zero, for example. Recurring decimals can be written as, for example, this recurring decimal is equal to 1/3. So any recurring decimal can be written as a fraction. So recurring, all recurring decimals, all terminating decimals, for example, 2.35 can be written as 235 over 100. So any of these would be a rational number. Anything that's not rational is called an irrational number. Set of all irrational numbers. And you've seen a lot of irrational numbers. For example, radical 2, 2 plus radical 3, e, pi. These are all irrational numbers. Anything that's in the decimal form that is non-recurring, it doesn't have a pattern, it just keeps going on and on, like the number pi or e are examples. And of course radical 2, radical 3 and any combinations of those kind of numbers would be irrational numbers. Now the set of real numbers, the graph of which would be the number line, it includes both the rationals and the irrationals. And of course any of these natural numbers or whole numbers or integers are rational, so everything is included. So the combined set of rationals and irrationals, so you would say you unite these two sets and that would be the set of real numbers. Every little point on this number line is a real number, and this is in the interval notation. The set of all real numbers is negative infinity to positive infinity. Now we'll look at examples of sets. Suppose I have the set A. Usually we use uppercase letters. 1, 2, 3, 4. Let's say the set B is 2, 3, 4, 5, 6, 7. So both these sets are finite sets. Now suppose I want to combine sets in a different way. Let's say I want to find A union B. What exactly does this mean? It means that it's the set of all numbers x such that x belongs to the set A or x belongs to the set B. So this is the mathematical notation for the set of all numbers x. So what is contained in A union B? All the x's that follow this rule, they either belong to A or B. It's possible they belong to both, which is fine. So let's see what A union B is. They have to belong to A, so let's write down all the numbers that belong to A. They also can belong to B. 2, 3 and 4 we've already written. So 5, 6, 7. So what we are doing is uniting or combining the sets A and B, and that would be A union B, combining all the elements of set A and set B and writing it down without repetition. Now what is A intersection B? Intersection is the overlap. So unite or combine is for union, and intersection is the overlap only. The condition is much stricter. So let's look at the set theoretic definition. It's the set of all the numbers x such that x belongs to A. We are talking about an overlap. So it has to belong to both, and that's why we use the letter and. X belongs to B. X belongs to A and X belongs to B. So that would be, let's look at A and B, the sets A and B. What's common? Let's look at what's common. 2 is common to both. 3 is common to both. 4 is common to both. So what is the overlap between the sets A and B? It's the intersection of A and B. So A intersection B is 2, 3, or 4. So when you unite or combine, so that's U, write down all the elements in both the sets without repetition. Everything has to be included. A intersection B is just the overlap. It's the intersection or the overlap.